Let's go. So today what we're going to do is we're going to take some notes. This is going to be the last lesson of notes. So my goal, I'm not sure if you guys were aware, but my goal was to do Friday was going to be test revision, and then Monday, and so not this Monday, next Monday was going to be the electronics test. Now, obviously, this is a little bit up in the air because it's like, who knows what's going to happen with the COVID restrictions, etc., etc. But that's still my goal. So if that's my goal, then today I need to finish off the last bit of content, which is actually not too much content, which I'm actually glad for, which means that our job is going to be relatively easy. I'm just going to talk about some extra components, and then I'm going to leave you guys with the rest of the time to work on electronics 3. I think that was the one that I said, but we'll talk about that in a sec. So Margaret Knight is today's Stolen Ideas. It's the final Stolen Ideas class that I have. She was an American inventor who created machines and other industrial things for everyday purposes. And in 1867, when Margaret worked at the Columbia Paper Bag Company, she found out that paper bags were weak and small, and so she decided to improve the paper bag by inventing this machine that allowed products to allow the production of square bottoms of paper bags. And this invention was most famous out of several inventions that Margaret painted. Margaret Knight's invention had been stolen by a man named Chris Sitwell. What did Chris Sitwell do? He had taken the idea of square bottom bags and improved them by adding pleated sides and made them fold and storable. So I like this. This is very interesting. It's one of those ones that's like, there's a lot of inventions that you hear about that you don't really think, that you don't really realize someone had to come up with that. And the paper bag is one of them. Someone had to come up with a square-based paper bag. And you might think, well, duh, that's an obvious extension. It's like, well, they already had paper bags, just like a bag, 2 pieces of paper sewn together. So the fact that, you know, someone thought maybe we could make a square bottle, we'll make it stronger, bigger. I think that's a really interesting idea. So yeah, disappointed that we don't get to find out what happened. Did she just give up? Did she sue the person for stealing the idea? Who knows? So today's lesson, we're going to be looking at other types of components in a circuit. Now, we've spent most of our time talking about, whenever we look at components in a circuit, we talk about the battery, we've talked about light bulbs, we've talked about resistors, and I suppose we've talked a little bit about switches. And then in the most recent topic that we just did, we just talked about the LED, the diode. Now, the main goal for us is to be like, well, what other circuits are there? And I'm also going to spend some time just making sure that we fully understand how the diode works. And before that, let's go backwards a sec to see what we did last lesson. So last time I had you guys, we were talking about non-ohmic devices. And when we talked about non-ohmic devices, we discussed that, you know, non-ohmic devices don't follow Ohm's law. What does it mean not to follow Ohm's law? So when something follows Ohm's law, it makes a nice straight line. And that nice straight line means that as the voltage increases, the current also increases. So as you apply more and more and more push, then you get more and more and more current. Now, then what we did is we looked at, well, what happens if you have something that doesn't follow Ohm's law? What if you have something that looks like this? Or maybe you have a circuit that looks like this, you know, whatever. It doesn't follow Ohm's law. Well, we said it's non-ohmic. How can you tell? Because it's non-linear. And if it's not linear, then it's not following Ohm's law. It's not having its current increase as its voltage increases. In this one, the voltage keeps increasing, but the current doesn't go anywhere. In this one, the current keeps increasing, but the voltage doesn't need to be increased. So it's not, the resistance isn't constant. So we said that we spent some time looking at what this would look like if we were to graph it. We actually spent, we plotted one of these guys. And we talked briefly about what the shape of it was. Then we spent the end of it. We spent a little bit of time looking at this, but not a lot of time. Just a quick review goes, this is the formula for it. There was no pencil here, so you didn't have to copy this down. And I just said you could flip these equations upside down, around, whatever you want. And then we ended on this big chunky slide here. Well, we didn't end on this slide, but we sort of finished up roughly around the side. I said a diode is a one-way component in a circuit, which means that the electricity can only go one way, from left to right. I said that the direction of the arrow is the way the current goes. I said the LED is a light emitting diode, and this the diode has a switch on voltage. Now, and after this, what we did is we did a couple of experiments using LED diodes and resistors. And these diodes happen to be LEDs, and we used a resistor. And one of the questions that I asked you was to tell me, why do we need a resistor? The reason we need a resistor is pretty much because of this. So this is a slide that I don't think I showed you, but I'm showing you now. These are the switch on voltages of most of the resistors. You can see here that, for example, let's look at red. So red switches on here. If we look at that, we'll call that 1.3. So 1.3 volts, red switches on. And then after that, it pretty much doesn't really, its current goes up. It does sort of look a little bit ohmic, but it's not really, because it shoots straight up. You can almost say that it's pretty much losing just between 1.3 to 1.5 volts. So if I was to say, plug this into a 12 volt circuit, right? If I was to plug a red LED into a 12 volt circuit, what do you guys think would happen? I would like you guys to either give me an answer out loud, or write it. If you're not confident, you don't want everyone to hear your voice, put an answer in chat. Tell me, what do you guys think would happen if I put a 12 volts through a circuit with a red LED that can only take about 1.5 volts? What do you think would happen? And Andrew, it gets cooked. Yeah, I want to know what would happen if I switched it on, Raymond. And what would happen to the... Does anyone agree with Andrew, or do we have any competing theories? What else? Give me something else before I move on. You can speak out loud if you want. You don't have to go to chat. If you don't know how to access the chat, you should see a little bar at the bottom which says chat, and you should be able to click on that. A little box should open up, and you should be able to type in, I think the LED will blank. Yeah, okay. So 2 people say cooked, and thank you. I'm going to leave it there then. That would be my guess too. The LED would be toast. Why? Because ultimately it would try to put 12 volts through, and that's going to put like hundreds of thousands of of amps worth of current, so it's going to be destroyed. So that's why when we were using those circuits, right? Firstly, I told you to use 6 volts, but even if you were to use 6 volts, that should technically cook the resistor. So what we cooked the LED. So what we did is you can still get this to work by hooking the LED up to a resistor. And so that means if you end up with a drop of, let's say, 1.5 volts at the LED, the rest of it, the other 10.5 volts, will be dropped over the resistor. And that's fine. It does mean that LED is not acting like a ohmic device, but yeah, just wanted to show you why we use the resistor for in the first place. We've got to make sure that the current, the voltage, has somewhere to get dumped, because ultimately the LED can't act as a resistor. Now, the diode can't act as a resistor. Now, I want you guys to copy this down. If you recall, when we were in at the very end of last Monday's class, I was like, okay, guys, I'm going to show you this, but I'm not going to get you to copy it down. So today I'd like you to copy it down. You guys can copy it down in your books. You guys can copy it down in a piece of paper and stick it into your books later on. I don't really mind too much, but this is the new idea. What I'm going to get you guys to do is I'm going to get you guys to draw this diagram here. And what I'm going to do is I'm going to give you guys, it doesn't have to be exactly like this. You can draw your LED, your battery just like this. But you can do a double battery if you want, that's fine too. And then what we'll do is we'll go through it. I'm going to give you guys about 45 seconds to copy this down. So from now, and then I'll start explaining what we're doing with this. For those of you guys that don't know, this on the left is actually called a battery, not. Whereas if you have just one of these things, like this, technically this is called a cell. I did not know that until I got much older, but a battery is actually when you have multiple cells together. So yeah, okay. So at this point, I'm going to assume that you've drawn this. If you haven't drawn it yet, that's okay. It doesn't have to be super accurate either. It doesn't have to be like, oh, I have to get my ruler, shit, where is it? Just want you to draw a basic picture of it. Okay, so now let's have a look. What's going to happen here? So let's draw the current. Now, a quick question for the chat or out loud. Is the current going to come out of the top or the bottom? Is it going to come out of the positive or the negative? Which one? Positive. Thank you, Nee. Top. Thank you, Jocelyn. Thank you for the participation, guys. Otherwise, I feel like I'm just talking to like nothing, you know? So yeah, it comes out of the top. So the current, I'm going to draw the current like this, okay? So it's coming out of the top this way. Why it's coming out of the top? Because it's the positive end. How do I know that's positive? One, because it says so, and two, because it's the long straight edge. So if I keep coming up here, can you guys see how this arrow here that I've just drawn is the same direction as this arrow here that's part of the diode? So that means that this will conduct current. So the current can come all the way back around to the end. And that means we have a completed circuit. If we have a completed circuit, this is another question for chat really quickly. If we have a completed circuit, does that mean this light bulb will be on or off? On. Thank you. Nice, easy one. Thanks, ladies and gents. So this light bulb will be on. So I'm actually going to draw some lines coming out of that. And I'm going to write on. Because see how it matches. So that's what we're going to do. Next up, we're going to do a counter example. So I want you guys to draw this one here. I'm going to give you guys another 45 seconds to draw that before I jump in. I'm going to change the color to blue. Okay, so we're going to start for the second one now. Second one now, guess what? Current's going to come out the same way. So the current's going to come up. And then here's the question. Does this arrow match this arrow here? What do you guys think? Yes or no? Oh, we've already got an answer. Thank God. I love it. I've just managed to screw up how. No, sir. Thank you, Ray. So if it's not going to match, would you guys think it's going to conduct current? Is this going to allow for the? No, it's not going to allow. So that means overall, this is like a break in the circuit. So therefore, this is going to be off. And the trick is that because it's going to be off, you would say this doesn't conduct current. You could actually say that the voltage drop over this resistor is so high, like the voltage drop over that resistor is so high that no voltage actually gets dropped over that that light bulb. But I'm happy with you guys just knowing that that's switched off. It's like a break in the circuit. So the first one is on because they match, the second one is off because they don't match. Well, what's the deal with the third one then? Well, the third one I'm going to start doing now. If you guys haven't drawn the third one yet, that's okay. I'll start to work on it now. So the third one, the current comes out of the top, and we can see that it matches, so we're all good. So that means the current is going to come back down through here, but then it doesn't match. So therefore it stops conducting current here. No current can pass through this section here. Or if it does, it's going to have such a high voltage drop over this LED that this light bulb won't light up. So this light bulb is going to be off. You might say, but sir, look, the current goes through this light bulb, whereas it didn't go through this light bulb. So just because the current goes through it, if the current can't complete the circuit, then it stays off. And even if the current can complete the circuit, like even if a little bit of current slips through this, there'll be such a small current that there won't be any voltage drop over the resistor, over the light bulb. So that's why we say that this is off. If you don't understand that, I'm happy with you just understanding that, hey, there's a roadblock, no current means no light bulb. That's all I want you guys to understand. I'm going to keep this slide up for about another, say, 30 seconds, and I'm going to jump to the next slide, which we've got some more examples like these, but they're a little bit more complicated. Okay. So, next slide. We're going to finish up our ideas of diodes. Now, these are 3 examples, but these are relatively just teaching us the basics of diodes. The next 2 examples are slightly more complex, and they're designed to sort of test your understanding. So this is the first one on the left. And then the second one, and what we're going to do is we're going to work out how this one would work. Now, if you want, I would suggest make your predictions. Actually, you know what? I would like someone to make a prediction in chat. It could be wrong. That's completely fine. I'm not going to roast you if you get it wrong. I just want you to say, what do you predict? Do you predict A to be on? Do you predict B to be on? Do you predict both of them to be on or both of them to be off? What do you guys predict? Give me a prediction. it can be wrong. In fact, it's good if it's wrong. Why does Mr. Green want us to be wrong? Because if it's wrong, that means you've got a chance to learn. Okay, cool. All right, so I've got some guesses here. Thank you, Anne. Thank you, Ray. Let's see if I can get one more guess. One more guess. What do you think? One more prediction. One more prediction, guys. Yep, cool. Thank you, Ilya. All right, so let's have a look to see if you guys, let's see how these predictions work. So we're going to do the same thing that we did last time, where I'm going to change to orange, and we're going to draw the current coming up. Now, you don't have to draw as many arrows as I do. I just like to draw these arrows just so that you guys can sort of see the current, but you guys can just do 2 or 3. At this point, we have an interesting thing happen. The current can either go down or it can go to the right. And if it goes to the right, it's going to go down this path here. Now, if we look at these 2 arrows, this one matches this direction, so it's going to go down. But this one doesn't match this direction, so it's not going to go down. As we go down, this one is going to go through, and then it's going to complete the circuit, which means that A will be on. But B will not be on, because even though, and this sort of starts to introduce you to the idea of like, oh, parallel circuits, you know? Well, we can have current splitting, but you still need to know which direction the current goes after it's split. So let's look at this. B is off and A is on. So that's exactly what a lot of people said. B is off and A is on. This is the last diode example that we're going to do to the right. And this guy is a bit of a beast. It's a bit complicated. It's not out of the realm of you being able to do it. I actually think there are some students here that could do it. But you're more than welcome to make your predictions in chat if you want. If you don't, that's okay. I'm going to leave. This is a bit complicated, so I'm going to get you guys to draw this. I'm going to give you guys about 30 seconds or so. And then what we'll do is we'll do this question. Oh, we've got some predictions for this next one. 2 people saying B is on. Okay, but you know, is A on? That's what I want to know. Is A on or is A off? Let's figure it out. A is off. Okay, so that's our predictions. Okay, so we'll have to see. Believe it or not, the first time I ever taught this example, I got it completely wrong, and I felt really bad for the students. Yeah. What is this? What do you mean, what is this? Raymond. What is what? These are diode circuits. I'm getting people, some people chose to predict what the circuit on the right is going to do. That's what the predictions were. Okay. Let's start. So we've got the positive end and the negative end of this. So this has got 4 diodes. So this is going to be some interesting stuff going on here, because there's lots of paths and avenues for this current to go. There's actually lots of branches too. So let's go. So as I go to the left, let's try and cut down the amount of arrows too. Let's do one there, and then we'll do one here. So then at this point, we've got the current can split. One's going to go to the right, like this. And one's going to go up, like that. Now this one conducts current because it's pointing the correct way. This one does not conduct current, so it's not going the right way. So it's going to stop there. The current's going to go through B, and then we get to another junction. So the current can either go up or it can go to the right. Now, if it goes to the right, it hits another diode, which does not match, so it's not going to conduct. And then it's going to get to this junction here. This is where I made a mistake back when I was teaching this in when I first started to teach this. The mistake that I made was this. I said, oh, at this point, the current's going to split. Some of it's going to go to the left, and some of it's going to go to the right. And then after a long time of looking through textbooks, I realized I did that completely wrong. Ultimately, this current has one goal. It wants to get back to the negative side of the battery, right? And it will walk down, it'll go down any electrical path, no matter how long it is, as long as it's getting closer to that negative, okay? So at this point, the current could go either left or right. But if it goes left, it's actually going further away from this negative side of the battery. So actually none of it goes left. All of it goes to the right. And this one is pointing the same direction. So it does conduct. And so it goes down. At this point, the current could go left or it could go down. But if it goes left, it gets further away from the negative. So it's not going to go to the left. It's going to go down. Which means that this is now our complete circuit, which means that B is on and A is off. That other trick, you might say, but so you didn't, like, what about in a parallel circuit? Remember, in a parallel circuit, the current still splits, but as long as there is a way for the current to get back to the start, then it will do that. It just so happens if, like, the current goes to the left here, it'll be going back around to a place where it's already been. It wouldn't do that if it's already, like, if it's got such a quick way to get to the end. So that's how sort of I think about it. It's like, okay, would the current, and you might say, well, why is it split upwards here? Because it's looking for another path to get to the end. Well, why didn't it go to the left? Because that will go away from a guaranteed path. So that's why B is on and A is off. So these are how LED circuits work. And the reason why I'm showing you these are because let me show you, pardon me for a sec. The reason I'm showing you is because these show up in the work that I've asked you guys to do. Let's have a look at the work that I've asked you guys to do, and then what we'll do is we'll move on to the rest of the lesson. But I just wanted to show you guys, if you weren't aware, that if we go to electronics 3. Pardon me. Down here, we've got, these are the questions that I asked you guys to do, and I handed this out to most of you guys. If you haven't got this worksheet, by the way, I'm going to put this worksheet up onto the Google Classroom so that you guys can actually work on it today afterwards. But if you have got it already, great. But if you go all the way down, we've got a section where you have to plot some non-ohmic resistors. So you just got to plot the y equals 2x. And you've also got so you've got this one where you got to predict what the switch on voltage, so where does it switch on. So for red, as I said, it's like between 1 and 1.5, I'd say about 1.4. So you can just read them off this chart here. But this section here is the stuff that we just did. So you guys can now do this. So for this one here, you can see the positive line. And this one would be interesting, actually, because you can look at that. You can look at that and you can be like, oh, well, the current's going to come up here. Some is going to go down here. Some is going to go down here. At this point, you know, the current wants to get back to the negatives. So the fastest way is going to be going here. But this one, who knows? It's either going to go this way or this way. It can't go that way. You know, hey, cool. You can work out that one relatively. But there are a couple of examples for you guys to do. Most of them are pretty simple. There's only like one or two like super complex ones down the bottom. You'll also need to know what a capacitor is, so I will explain what that is in the next couple of slides. But that's going to be what you guys will work on after this lesson if we get there. So let's get back to the PowerPoint though, because I have some more. So back to it. So I've just sort of gone through this stuff here. So, and I've talked about diodes, but like, speaking of capacitors, that's the very first one that I'm going to show you. So capacitors, I'd like you to jot this down with mine. We're not going to go through many components. If we guys think, oh my God, I'm going to have to learn every single component. No, we're just going to talk about some of the main ones. And capacitors are one of the ones that we don't get to talk about very often. So capacitors are two separated metal plates. It's actually they're one of the most simple devices. But they build up charge and don't conduct electricity. Like, why the heck would you have a device in a circuit that doesn't conduct electricity? The reason is because they release this charge in a short pulse of high current. The values of capacitance are measured in farads. Let's talk about how this works. So if I had two metal plates, right? Let's just say I have electrons in my circuit being pushed. And this part ends up with a huge negative charge because all the electrons are being pushed onto this metal plate. Well, that means that on this metal plate, you know, all this metal plate, because nearby, it's going to be completely positively charged. Why? Well, because the reason it's going to be completely positively charged is if this is negatively charged, all the electrons are going to be pushed away, and so it's going to make this charge. So what you end up with is you end up with a huge charge. It's like and that huge charge is a large amount of energy. And it just so happens that they don't conduct electricity because obviously none of these electrons can move over. So in that picture where you've got that capacitor, it's not going to conduct electricity. But what happens is that when you turn off the device, suddenly there is nothing forcing these electrons to be on this plate. So when you turn off the device, you are going to get a huge amount of electron flow out of this wire. And that can actually be, and that is actually how a capacitor works. The huge amount of electron flow leads to a huge current. So let's see. Pop quiz then. Does anyone know? This is actually going to be very, very unlikely that anyone's going to get this correct. So if you do get this correct, you're amazing. Does anyone know why would it be good to have a huge amount of capacity, a huge amount of voltage, or a huge amount of current? What device would need a huge amount of voltage or a huge amount of current in a short amount of time? I can think of a lot of examples, but I want to see if anyone can get one of the main ones. Why does anyone know why a device would need a huge amount of power? Can you even think of a device that would need a huge amount of power? Just a suggestion, just an idea. I just want one idea just to make sure Oh my God, Peter, you're amazing. Yeah, defibrillators would be one of the actual examples that this would be used for. Can someone else tell me what a defibrillator is? Someone other than Peter. What is a defibrillator? Does anyone know? Or is it just Peter? Yeah, Brian's close. Brian says it's a device that stops the heart. I guess technically you're right. Defibrillators are devices that you put on someone's chest, and the idea is that you put a huge amount of voltage and current through their body to try and get their heart started at a normal rhythm, or to try to, essentially to try and get their heart to work at a normal rhythm. Now, you can't just, put a current through someone's heart. You have to put a high current. So that's what they actually say charging. What are they charging when they're charging the defibrillator? They're charging some capacitors. So that's exactly what they're charging. Anyone? Okay, I'm going to give you guys the rest of some of these other examples now. So another device that requires a huge amount of current for a very, very short amount of time, probably not one that you guys would guess, is a camera. But not just any part of the camera flash. So the camera flash is actually part of a capacitor. So why is it part of a capacitor? Because what happens with the camera flash is that it builds up a charge, and then it will set off all that charge at once, which allows for a bright flash rather than a regular sort of light. In the old cameras, you used to actually be able to hear it charge up. Sometimes you actually might be able to hear in, if you ever get a disposable camera, you actually hear it go wee, and then it'll go flash. The other place that you guys probably won't know where it's used for is it's used a lot in lasers. And that's because in order to get something to shoot out a laser, you need to have a high amount of current. But they're also used in lots of other places. But at the bottom of this page is a link to a person called the Hacksmith. Love his channel. He actually made a railgun with capacitor. You might say, why do you need? How does a railgun work? Well, in order to get a railgun to work, you need a lot of current, and you need a lot of current happening all at once. So he had these really big capacitors that he used. And I just watched yesterday a way that people use huge amounts of capacitors to essentially put a current that's so large that it crushed a coin into like a little brick. So yeah, capacitors are kind of fun. They're also incredibly dangerous. So there's a capacitor inside of your microwave. And the reason why they're so dangerous is because they keep their charge after the device is switched off. So that means if you touch, and this is one of the ones where which I find really interesting, but also scary as hell, is that some people will find, they'll be like, this device is unplugged from the wall. That means this device is safe. And so they start unscrewing things, and you can actually still get electrocuted from a microwave after it's switched off, because the capacitors will deliver a large enough shock to, because they've still got electricity stored in them. If you think about it, capacitors, they're like little batteries. They keep a device going after the device is switched off. The last place that you guys can maybe see a capacitor is pretty much any sort of electrical device, but the one that I always talk about is TVs. So when you guys take a TV, right? When you guys take a TV, there's usually a little button on the bottom of it that's an LED, and the red LED is usually to be like, yeah, this TV is switched on. And when you switch the TV off, that red LED turns off. But here's a question. Did you guys ever notice that that red LED, it switches off, but it doesn't switch off right away. It actually takes a little bit of time to turn off. Does anyone ever notice that? If not, strongly suggest having a look at it yourself. Try and next time you have a TV, switch it off, look at the red LED. And it doesn't switch off right away. The reason it doesn't switch off right away is because of capacitors. The capacitors in the television take a while to get discharged. Now, what do capacitors look like? These are what they generally look like. There are different types. The one that I'm most used to seeing is probably this one in the middle. This one here. And yeah, I have a couple of friends that have repaired computers by just replacing the capacitors. Capacitors get blown up. When a capacitor gets blown up, this top part here bulges out. So it goes from looking like this to looking more like this. And so when that bulges out, you can actually be like, okay, that capacitor is dead. So you can replace it. And I've actually seen people replace like really expensive laptop monitors just because they've gone, oh, I reckon that it's the capacitor. Hey, look, this this 10-cent capacitor is broken. They fix the 10-cent capacitor and they have a brand new working computer screen. So just like if you do get good at electronics, you guys can actually identify these capacitors and fix them up. So that's capacitors. Now resistors is the next one. Now, we've already spoken about resistors. I've already discussed what resistors are. So I'm only going to spend a little bit of time talking about these because like we've already gone through them. So resistors are specified in ohms. They measure ohms. You can also measure them in kilo ohms or mega ohms. Mega ohms are millions of an ohm. Kilo ohms are thousands of an ohm. Now, resistors are not polarized. You can plug resistors in any direction. This is also the same, by the way, for capacitors. Capacitors are also not polarized. And they can be installed either frontwards, backwards, or whatever. They are ohmic devices. We already know that because they follow Ohm's law. And there are two symbols for them. In Europe, they like to use the square boxes. In USA and Japan, they like to do the squiggles. I like both of them. I like the squiggle one because it's that's essentially, as I think I may have told you, what a resistor looks like. A resistor, if you were to break down a resistor, it actually just looks like a big coil of wire. And the reason that it's a big coil of wire is because it, the longer the coil of wire, the more time it takes electrons to go down the wire, so therefore the more resistance it has. So that's why I like the USA Japan version of it. But to be honest with you guys, I find myself drawing the European version the most, even though it doesn't really look like what a resistor is. The reason for that is resistors are the most common component in a circuit. So because of that, you want to make sure that your most common component is easy to draw. So a square rectangle is pretty easy to draw. Last but not least is on the right. Now, I'm not going to get you guys to copy this down because hell, that'd be really difficult too. But this here is the color code. Now, on every single resistor, you will see a small set of lines. These lines are very, very, very tiny. But if you can look at those lines and count how many there are, you can actually get an idea of the type of resistor. So if I was to look at this one here, even though the answer's already been given to me, I can read. This has got 4 lines. So that means I'm going to look at the first, the second, the fourth, which is the multiplier, and the fifth. If I have 5 lines, I'll look at every single one. Now, how do you actually read a resistor? Well, you look at the first color. The first color is green. So green, that's going to be 5. So 5. Look at the second digit. So that's blue. So the blue is going to be underneath. 5 is going to be 6. And then I skip the third one because I've only got 4 lines. And I go straight to the last one. The last one is orange. So orange is times 1,000. Okay, whereas if it was yellow, it would be times 10,000, green times 1,000,000, and blue would be times 10 million. Okay, and then the last line is the error. So plus or minus 5% because it's gold. So what does that mean? That means this is 56,000 ohms plus or minus 5%, or 56 kilo ohms, which is what it says here. And 56 kilo ohms, what's this plus or minus 5%? That means that it could be a little bit more. It could be 5% more would be 60 kilo ohms about, and 5% less would be about 50 kilo ohms. So it could be a little bit off. If you have something that's brown or red, then that's got a much better tolerance. That means it's less error. It's 1%. That'd be the difference between 57 and 56.5. But you don't need to know how to read that. I'm just showing you guys how to read that just in case if one day you end up at a circuit shop and you'd be like, well, what power is this resistance? You could go, well, you have seen this before. At the bottom one, you've got 3, because it's 1, 2, 3, 4, 5 lines. Use every single one. You've got yellow, which is 4, purple, which is 7, black, which is 0. Then the multiplier is times 100, and then the error is brown, so plus or minus 1%. That means we've got 400. We've got 1, 2, 3 zeros, plus or minus 1%. So 47 kilo ohms. Cool. So that's resistors for you. Now, you can get special kinds of resistors, right? Not all resistors are just your boring, basic, run-of-the-mill resistor. So you can have resistors called variable resistors. Some components change their resistance depending on conditions. What are those circuits? What are they? Well, we can talk about something called a thermistor. A thermistor has resistance changing depending on temperature. A photoresistor has its resistance changing depending on light. These types of circuits can be used to, these types of resistors can be used to manipulate circuits. Now, after you've done that, your goal is to write in chat or online. We need to come up with 3 examples where thermistors and where photoresistors could be used. 3 examples of where these are used in everyday life. 3 electrical devices that, you know, measure temperature or somehow, or measure light somehow. On the bottom, you've got the symbols. I would suggest for the symbol that you would draw this one here and this one here. If you want to draw all of them, be my guest. But those symbols on the left and the right are the ones that relate to the square. And they're the ones that we use the most often. I'm going to get you guys in chat. Once you copied it down, give me a device that would use a thermistor. All right, who can give me a device that that uses a thermistor? A device that uses temperature as part of its operation. I can think of 10 examples. Can I think of 10 examples? Probably not. I can think of at least 5. A heater. A heater is a great example. Thank you, Art. Yes. Heater is an example. I'm going to add that to my list so you guys can add it. So how does a heater use a thermistor? Well, it measures the temperature. So then it will be like, hey, it's too cold. So therefore, I'm going to send out a weaker voltage. So therefore, the computer can be like, hey, this is getting a weak voltage. That must mean it's cold. That means I should probably put the heater on. Exactly. Can I get 2 more examples so we can write all these examples, so we can put some examples down that book? What are 2 more examples of things that might use a thermistor? Good job, Arm, by the way. PC, yes, good job, Brian. PC components. We're going to use PC/CPU. Now, it just so happens that the CPU is the brains of a computer. If the CPU gets too hot, then it will, I mean, yeah, there are other components as well. If the PC gets too hot, then what it will, if the CPU, which is the brains of the computer, if the CPU gets too hot, then it's going to start melting. It's going to start getting destroyed and degrade. So what happens is that as you do a greater and greater load over the CPU or even over other components like a GPU or whatever, then it'll be like, oh crap, I'm getting too hot according to what this thermistor says. And so then what it does is it goes, I better turn a fan on, and so, or water cooling or whatever else you've got in your computer, and that will cool down your computer. What else have that's a really good one as well, because it's like, in the first one, the heater is like what we want to know the temperature. We want to change the temperature. The second one, we want to change it to bring it down. If I got a third example that I can put on this list, what's the third thing that would have a thermistor in it? What's the third thing that measures temperature? See if we can get one more. A fridge. Perfect. Fridge is great. Now, a fridge actually has a thermistor in it because if it gets too cold, if it gets too hot, then it needs to turn the compressor on and to cool the fridge back down. 3 examples for thermistor done. Now, let's say we give 3 examples for a photoresistor. When would it be good to be able, when would we need to measure the light of something? When would we need to measure how bright something is? When would that be useful? I can think of a couple, maybe not as many as for them. So if you guys can't, I just want one from you guys. If you guys can't come up with one, then yep. But Andrew's come through with the goods. Street lamps are great examples. So street lamps have a light sensor that turns on. It says, hey, it's getting dark. I better switch on. My next example that I'm going to give you guys for free, because you guys might not know, would be a camera. Camera ultimately is a massive set of photoresistors. They measure the brightness of different things. And I guess the third one here, which I could use, I could choose any of them, but we might go with We might go with automatic doors. Some automatic doors use photoresistors to make sure that they can see, oh, wow, there is something big and black and dark blocking the light entering my photoresist, my circuitry. So therefore, there must be something in the way of the door. I better open the door. But there are many places you can use these. And that's the cool part about these types of circuits, is that once you start to be able to figure them out and put them in circuits, you can make your circuits be smarter. You can be like, oh, now my circuit, like I used to have a circuit that would switch on a light when it got dark. I could switch on a light and switch it off, but now my circuit switches on the light when it gets dark. Like, cool, excellent. You've actually made your circuit respond to something. Yeah, auto brightness feature on a phone is another great example. So even auto brightness feature in cars is another example. So when you're in a car and you go, the car goes, hey, we've gone into a dark tunnel, I better put the lights on. That's using a photoresistor. So when your phone goes, hey, I better switch the lights up because it's getting dark in this room, that's, doing the same thing. It's using a photoresistor. So all of those are different ways. So there's just different types of resistors. I've just talked about those because they're on this slide here. I don't know why I've got two slides for that. Nah, stuff it. Do that. It doesn't matter. And then, yeah, I'm just going to wrap up on the last little bit on this page here. I don't want you to copy this page down, but these are a bunch of extra components. But I think most of them we've already talked about. Probably one that we haven't spoken about would probably, that jumps out at me, would be these two, the microphone and the loudspeaker, because they are, but you sort of already know what they are. These are a bunch of different components. We've got here's our light depending resistor. Here's the thermistor. You've got pretty much everything here that we've already discussed. They're probably the only things we haven't discussed. So that may be in inductor, but it doesn't matter really too much. But they're the only other components that I wanted to show you guys. So I wanted to show you guys those just because they show up a lot in regular life. This last slide, actually there's no pencil here, so I'll talk about this last slide anyway. I will warn you guys that the resistors have different types, right? Obviously, if you're going to put if you've got a 2 ohm resistor, right, and you've got that wired into a circuit that's got 240 volts, that resistor is not going to last very long. So the resistors determine, you can look at a resistor and you can look at how much power does that resistor need to take. If it doesn't need to take much, you can use a little tiny resistor. If it needs to take a lot of power, then you will use a big resistor.